find these beta i's. This is what I would say. Okay, so um, let's let's move to the next what is called an autoregressive process. Okay, so a time series xt is called an autoregressive process of order r, denoted by ARP. Okay, so ARP if xt equals alpha 1 xt minus 1 plus dot 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 alpha r x t minus r plus zt, and where zt is normally distributed with mean 0 and variance sigma square. Okay, so if this happens in some time series, then we say that it is an autoregressive process of order uh, order r, ARR actually. Yeah. Okay, now we have already seen one autoregressive process, the random walk that we did. Okay, so xt equals xt minus 1 plus epsilon t, right? So this is a, an example of an autoregressive process of uh, order 1, right? This is an autoregressive process of order 1. But we know that this one is rarely stationary, right? We have also seen that this one is rarely stationary. So, I mean, in fact, never is stationary, this one. However, when we have some coefficients here, alpha I, so if I had something like xt, alpha I xt minus 1 plus epsilon t, then we can actually put some conditions on alpha I and get that xt is stationary. So the question first is, when is these kind of autoregressive processes stationary? So let's take the simplest example of autoregressive. So let us look at AR1 process. Okay, so what happens if we have AR1 process? So suppose this process is given by some xt equals xt minus 1, some alpha 1 t minus 1 plus epsilon t, and where epsilon t is normally distributed with mean 0 and variance sigma square. And also we have seen an autoregressive process in the past also, other than random variable, other than random walks. Here, this one here is also an autoregressive process. Actually, what is the order of this autoregressive process? Can anyone tell me? So here I have zt equals summation I equals 0 to infinity some beta I xt minus I. So you see that what am I saying? Oh, I'm sorry, no, I made a mistake. It's not like that. Okay. Just one second. I'm kind of confused now a little. Okay, so no, what I was saying was not correct. So, let's go with the definition of AR. So let's see what happens in the case when we have autoregressive process of order 1. So equals alpha 1 xt minus 1 plus epsilon t. Okay, so this is an autoregressive process of order 1. Okay. Now we can do the same thing that we did with MA process here, trying to invert the process. So, so you see that what I can do here is I can write xt as alpha times alpha xt minus 2 plus zt minus 1. Okay, plus plus so in my notes I wrote zt, so let me write here as zt. Okay, so what I can do is I can replace xt minus 1 with alpha xt minus 2 plus zt minus 1 plus zt, right? And so this will be alpha square xt minus 2 plus zt minus 1 plus alpha zt minus 1 plus zt. And I can do again here the same thing. So I can replace this by alpha square x t minus 3 alpha xt minus 3 plus zt minus 2 plus alpha zt minus 1 plus zt. So, and I can continue in this way. So finally what I will get is summation I equals 0 to infinity alpha to the power I z t minus I. And this we can do when provided we have mod of alpha less than 1. Okay, this we can do when mod of alpha is less than 1. Okay, so what do you get then? So if you, when you start with an autoregressive process of order 1 and you do the same thing that you did with the MA process, you get something like this. xt equals summation I equals 0 to infinity alpha I z of t minus I, right? So what is this one? So what is this? What can you say something about this process here? Xt equals summation I equals 0 to infinity alpha I z t minus I? What kind of process is this? We have already seen this one.
It is something like that one, minus theta to the power I.
Actually, you see, this is a moving average process of infinite order, right? Is this clear that this is a moving average process of infinite order? So, should I go back and say it is an infinite? Right? So Ramdas says that it's clear that it is an infinite order moving average process. And yes, it is actually clear because you see that how would you write a moving average process of infinite order? It will be xt, which depends on infinitely many independent normal random variables, right? So this will be, but we can do this when alpha is the modulus of alpha is less than, is what I'm saying. Okay. Okay, and we can do the same thing. This here we can do the same thing with backshift operators also. So we have this xt equals alpha xt minus 1 plus zt. So I can write it as alpha b xt plus zt. So then xt will be equal to zt divided by 1 minus alpha b. And this will be then summation this will be then summation 1 plus summation, but this will be equal to 1 plus alpha b plus alpha square b squared, so on, plus and so on. So zt. So if this can be done if mod of alpha is less than 1. Okay, so this will be then zt plus alpha zt minus 1 plus alpha square zt minus 2 and so on. Right, so this is what I will get here. Summation alpha to the power I zt minus I. Okay. So the question is when is AR1 process stationary, or the weakly stationary? We have been using weakly stationary. So when is this process weakly stationary? So because if it is in this form, then we can't really say about stationarity. But because we cannot really measure the variance of this, but in this case we can actually do that. So first of all, the mean of xt, this will be 0, right? Because it's each zt has mean 0. This is what we started with here. Each zt has mean 0. So the mean of xt, or actually I should write expectation here. Okay. So the expectation of xt is 0. And what is the variance of xt? The variance of xt if you look at this here, it will be tell me if I am right, sigma squared times 1 plus alpha square plus alpha to the power 4 plus so. Okay, all you have to do is to take the expectation of xt squared. So when you do expectation of xt squared, we will get this sigma square of 1 minus alpha square, 1 plus alpha square plus alpha. So when will this converge? This variance of xt, I can write this as sigma squared times 1 over 1 minus alpha square, given mod of alpha is less than 1, or alpha square is less than 1, but we already have mod of alpha less than 1, right? So then it will be constant. And what about ACF, the autocovariance function of this? So the autocovariance function will be gamma k, which is expectation of xt into xt plus k, right? So this will be the, and so we get expectation of summation alpha to the power I z t minus I. Times summation alpha to the power j z t plus k minus j. Right? So I'm just replacing here xt and xt plus k. And you will see that what will be left. So when we have zt and z, so whenever zt and t something else is there, we get 0. So we'll be left with sigma square summation I equals 0 to infinity alpha k plus I, k plus I here, right? So this will be alpha to the power k sigma square divided by 1 minus alpha square, and given that mod alpha is less than 1. Okay, so this gives us a sufficient condition for an autoregressive process of order 1 to be stationary. So we have the following sufficient condition for an AR1 process to be so xt equals alpha xt minus 1 plus zt, where zt is normally distributed with mean mu and variance sigma squared, is stationary if mod alpha is less than 1. Okay. So I will also give you the written notes, but I hope some of you are following this. But actually, you know, suppose we already knew that a given AR process is stationary, then we can actually find the ACF. Just we don't have to really invert it. We have to find we can find autocorrelation function directly. Let's see how we can do that. So if suppose we are given, we somehow knew, I'm assuming that the time series is stationary. Suppose AR1 process is stationary, then we can find ACF directly from the definition. And how do we do this? So we know xt equals alpha xt minus 1 plus zt. Now all you need to do is to multiply by xt minus k on both sides. So if I multiply by xt minus k on both sides, I get alpha xt minus 1 xt minus k plus zt xt minus k, right? And now if I take the expectation on both sides, I get expectation of xt minus k, xt equals alpha xt minus k, xt minus 1, expectation here, plus expectation of xt minus k zt. Right, and this will be 0 because zt has expectation 0, so this will be 0, and this will be, what is this? This is gamma of minus k. I'll put that gamma of minus k here. And this will be alpha times gamma of k minus 1. Okay, but gamma of minus k is gamma of k, so gamma of k will be alpha gamma k minus 1. So you see that we get a recurrence kind of relation, right? So gamma k equals alpha gamma k minus 1. And also gamma 0 is sigma squared. So this means that we can solve the recurrence relation here and we'll get gamma k equals alpha to the power k sigma squared. Okay. Is this clear? I mean, who can say it is clear? Is there any problem with this so far? So what we can do is we can go through this again in the next class if you want. Yeah, you want to go through this again in the next class and do some programming, then we can do that. Okay, so again we will, those who want to see it again, we will do some programming in the next class. Okay, and I stop here today. Any